Okay, so in this video, I'm going to solve example 2.4, and I'm going to calculate the force on a submerged curved surface in this one. So this question says, the curved gate shown in the figure is 9 meters wide. For part A, calculate the horizontal force applied by the water on the gate and its location. For part B, calculate the vertical force applied by the water on the gate and its location. Okay, so let's start with part A. And as I mentioned in the lecture about curved submerged surfaces, when we're breaking this problem down into its horizontal components and its vertical components, when we solve these horizontal ones, that's just exactly the same as solving for a flat plate. We just project this surface onto a flat surface. So we start by solving in the horizontal direction. And as I mentioned, you could imagine we have a viewpoint from the side like this. So we're looking in this direction. And then this gate is just going to appear as though it's a flat gate that's projected like right against this purple surface here. So I'm going to start by labeling the coordinates, and we're going to keep these consistent with the way we've been solving so far. So the y direction is down like this. X is into the plane, so into the page that we're looking at. And we will see the z direction here, which we'll need now for the vertical component. So first things first, we pick which method we're going to use. In this, I've shown you in previous examples using both method 1 and method 2, but because we've solved many horizontal questions already, I'm going to use method number 2 here. And as I begin, I want to just give you a reminder. So what we're doing here with these examples is, as we go through this, focus on your understanding of how this problem is solved, because there's going to be quite a number of different ways that we can ask this question. And so to make sure you're really understanding this the way a designer would, the way we want you to when you're finished this course, is to make sure you're not memorizing. So you're not just memorizing formulaically how to do this problem, but you're actually more deeply understanding how this problem is solved, so you can solve any number of questions. Okay, so for method number 2, our governing equations are as follows. And similarly to previous problems, we chose these equations because we have an atmospheric pressure force pushing against the back of this gate, which cancels off the atmospheric pressure from the surface. And so we can just use gauge pressures in these equations. Okay, so I'll draw a quick figure here. From the side, our gate's going to look like this. Okay, so I'll sub in here for the force first. So looking through these variables, it's density we know, gravity we know, hc, so that's the height of the centroid. So I can get that centroid value from a table like the one that I've shown here. So we see that c here is labeled as the centroid, and then the y value of the centroid here shows us that it's just in the middle of the plate. So I can sub in for everything then. Okay, now I just plug those in. I recognize those units as newtons, so then I can rewrite this as 397 kilonewtons. Okay, now for the location, I can again just sub in, and I make sure I read my table values correctly here. So I have the y centroid value, which is just halfway down the plate. Now I read off my table, same one we used before for a rectangle. So for Ixx at the centroid, I can sub in here. And then I'll simplify it symbolically first, using base and height. And then I'll cancel these off. Okay, and that's that for the horizontal forces using method number 2. I'll just do a quick check here to make sure it seems correct. So on a rectangle with a height of 3 meters, we know the centroid would be at the middle here. So based on my coordinate system, y starts from the top right here. And I know my forces at the bottom are greater because my pressure is greater, so I expect my location to be lower than that centroid point. We look here, it's 2 meters, which is definitely lower than halfway, which is of course 1.5 meters. So that all makes sense. Okay, so now we can do the vertical component of this force. And this is the new part here we haven't seen in previous examples. Okay, so I'm going to show this again in two methods, and the reason for that is because method number one is very simple, and you may come across cases where it just doesn't work due to geometry constraints. So for method number one here, I'll list that as the volume method, and we'll just list that equation that we derived in the lectures. Very, very simplified equation. And so when we have geometries that work for this, this is by far the more simple way to solve this question. Now, if we look at our problem, we'll realize we have a little bit of an issue. I'm going to schematically sketch out our problem here at the side. Okay, now the issue is that volume, the V in that equation there, we described as the volume above the surface. But in our case, there is no fluid above the surface. So we have to do a simple thought exercise here to sort of figure out, well, how can we calculate this if there's no fluid above our surface? So we have to see what it means, what these vertical forces actually mean. So I'm going to show you another way to describe this, and we'll say this picture here, which is our actual problem we're solving, is actually equal to, and I'll draw out two schematics here that we can think through. Okay, now I'll draw out the forces here to help us understand what we're looking at. So in our actual scenario with our real gate, we would have a force from the fluid. We know the pressure's acting on the bottom of this gate, so we expect an upward force like this as our vertical force. But as I mentioned, we have no fluid above this gate, so we have to think through how we can do this calculation otherwise. So in the next picture I've shown here, we imagine that there's fluid filling the space above the gate and below the gate. And I'll label this as a no force situation. Because we could imagine if now you're looking at the forces on that gate in the vertical direction, the forces that are above the gate and below the gate would actually balance. And so in this type of situation, we would expect there to be no actual net fluid forces pushing on the gate. So we'll call that the no force. And then in the picture on the right there, we have the case where if there was just fluid filling the space above our circular gate there. And in that case, now we know how to calculate that one. We would expect the vertical force downwards like this. And we can see from the drawings, when you're looking at the no force case, if you subtract off the case of the forces of the fluid above the gate, you end up with the case that we're dealing with, right? So a trick to calculate the forces here is to actually just look at this case of the fluid above the gate, and those liquid forces above the gate there, they must be balancing the forces that are below the gate. Right? So we can just calculate those fluid forces above the gate there, then flip the direction of the force, and we know that that must be exactly equal to the forces that are pushing on the bottom of the gate. So for our volume then, our gate is just a quarter of a cylinder. So we can substitute for volume in here as the pi r squared over 4 for the quarter of the circle, and then multiplied by the width of the gate, which is given in the question as well. And then we just simply plug in. Okay, 623 kilonewtons, and that is that. In many orientations, you will have fluid above the gate, so you don't always need to do this thought exercise, but it is sort of neat to see how the forces on each side of the gate balance and how you can use the volume of fluid above the gate in each case to always get those vertical forces. Remember this 623 kilonewtons also, because we did that, we have to remember that it's pointed up in the upwards direction against the gate and not downwards. Okay, now I'm going to show you another method here. And this is an integral method. And now you can imagine that method I've just shown you, that's really simple. You should always do that when you have simple geometries, but you're not always going to have gates or surfaces as your curved submerged surface that are perfect cylinders like that are geometries that are really simple to calculate the volume for, right? So if your gate is some other shape, or for example, if the gate is a cylinder, but only a portion of it is submerged under the surface, you're going to need another way to calculate this. So I'm going to show you this method here. And so we use our other formula from the lectures. And now we're going to need to substitute. So again, I'll need another picture here of what's going on, just to make sure it's clear. Okay, now there's a few different ways we can do this integral. I'm going to use cylindrical coordinates because it's a bit easier, but I'll walk you through all the steps. So firstly, to substitute into this, we'll note that dAy is just a projection in the y direction. So to go from dA, which is along the curve there, to dAy projection, we're just taking the cos theta times dA. Okay, now I've actually added a little sketch here to show the details exactly of how I got that, because I've been asked in the past a number of questions about exactly how to go about each of these steps. So I'm going to show it in detail here. So here's a sketch where I go through exactly the method of how you convert between the dAy and the dA. Similarly, for our height there, we can see the height direction. If we want to convert the height into our cylindrical, we note that that's r cos theta. I can also trace that triangle out in green so we can see what that looks like. Or if it's easier for you to see on the other side, like that as well, that makes it a little more obvious, I think. And then we remember also, probably you've seen before in calculus, but I'll do it all again explicitly so we can see it all out here, is that dA is equal to the width times the radius times d theta. So it's the area of that surface that we're looking at there times the width of this cylinder, so that'll give us that area there along the curve. Now, just as a side note here, I mentioned there's many ways to do this. Some people prefer to stay working in a Cartesian coordinate system, and I've seen students solve it successfully this way on exams as well. So you could also break down dA as w dz, and then note that the equation for a circle is r squared equals z squared plus y squared. And I'll just circle that in yellow, so that's just an aside there. I'm not going to do it that way, but just for full completeness here. Okay, now we're going to solve it in the cylindrical coordinates, so I'll just go and sub in all the relationships here and pull out the constant terms from outside the integral. And 0 to pi over 2, so you remember we're working in radians there, and as I've labeled the figure here, so as I've labeled theta here in our figure, it's going to go from a value of 0 to a value of 90 here, which is pi over 2 in radians. Okay, now we just solved this. You can use integral tables is what I like to use. All these integrals have been solved for us. So I'm just going to sub in the answer here. I'm going to do it in 2 steps here. I'll break down cos squared theta into its cos form, and then the integral I think will be a little more obvious. Okay, now I just sub in for the theta values there. And that matches what we solved for above. So I'm just going to stop there, and now you have all the mathematics. And as I mentioned, more complicated examples may not go from 0 to 90, or they may have a more complex geometry or curve. So now you've seen the method. Now you can understand what to do if your fluid level's a little lower and you maybe you integrate from 0, to pi over 4 instead of pi over 2. So this can serve as an example now of how to do these questions when the geometry's a little more complicated. But we see that it matches our answer from above, so I'm going to stop there and I'm going to go ahead and solve the location. Part B of this question asks for location as well as the force. Okay, so now we need to find the location for this vertical force. So we set that up similarly to what we've been doing for the horizontal force. So Z prime is what we're looking for. Z prime is going to give us the location of where the vertical force is acting. And on the right-hand side, same integral, except we multiply that by Z. So we just have to sub in z. I'll do a sketch here on the side so we know how to sub in for z in our cylindrical coordinate system. So from the sketch there, we can see that a z is equivalent to r sine theta, because sine theta is our opposite over our hypotenuse. Okay, so I'm going to go ahead and sub in here and see what we end up with. Okay, so I've taken all the terms that don't depend on theta out front of the integral here, and now we see we're just left with another trigonometric integral there. So we can just go to our integral table, and it'll have that integral solved for us. So I'll sub that in here. I'm going to substitute in for cos cubed theta. Okay, now we sub in the pi over 2 and the 0 limits there. The pi over 2 ones make it go to 0, but then when we sub in 0, that term in the square brackets becomes -1, so we're just left with the following. Okay, and a reminder from above that this expression is actually equal to z prime times fv. So when we want z prime, we have to divide the right-hand side by fv. So I'll substitute that in here. And then I'll just simplify. And the unit is in meters. So subbing in for that. Okay, our location is 1.27 meters. Now I'm going to draw this in. Normally on exams or quizzes here, we'll always ask you to draw these in. It's really important, right, for our understanding that we can actually draw these forces so we know physically, like we really have a physical understanding of where they're acting. Because ultimately that's what our designs are based on, right? So I'm going to scroll down here to the figure, and then we figured out the direction of our vertical force from the thought exercise above, and now we have 1.27 meters in the z direction. So I'll redraw the coordinates first. Okay, and it's really important you get your coordinates right and you make sure you're understanding these, because that's another big issue we see in exams where people will solve for a y and an x and not really understand where the reference point is or what exactly this distance means. So firstly, for completeness, we could just write something here like in this x direction, because you don't have pressure changing along the x direction, these forces all act at the same point, like right in the middle of the width of this gate. So we could just write, x. And that's sort of fairly obvious. So more interesting here is the vertical force. We mentioned it's 1.27 meters along the z direction. Our radius is 3 meters, so that is going to be somewhere a little less than the halfway mark. So I'll draw it right here. Okay, so that's where our vertical force is acting. Now I need to scroll up and remind myself where the horizontal force was. Okay, 397 kilonewtons and 2.0 meters. Okay, so the coordinate axes are there. So 2.0 meters now is going to be a little farther down below the halfway point. And the force is acting in the horizontal direction, so I'll draw that in here. Okay, roughly right there. And as I mentioned, that's a really big part. We usually give generous grades for being able to draw that in, because it's a really important part of solving this question, right? It's not just about the numbers, it's about understanding like what it all means and how it really comes together physically. Okay, so there's our solution for a curved submerged surface. I showed you a few different strategies there, from the really simple cases where the geometry is really straightforward to the more complex cases where you could use some of the integral methods. And hopefully that helps you out in understanding how to do these curved submerged surfaces.
Bye-bye.